What if you are not the only you? Our entire universe might be just one page in an infinite cosmic library, a single possibility in a sea of endless realities. Today we are exploring the compelling scientific case for parallel universes, diving deep into 25 distinct reasons why many physicists believe we are not alone in the grand scheme of existence. By the end, you will understand the profound evidence that our reality is just one thread in a vast, multidimensional tapestry. We will uncover why the laws of physics might be different just next door, and how every choice you make could be spawning entirely new worlds. What is the one thing you would ask your parallel self if you ever got the chance? Our cosmos might not just be vast, but truly endless. The first powerful reason scientists consider parallel realities comes from the sheer scale of everything. If the universe is infinite and roughly uniform, then the arrangement of matter and energy cannot be unique. Every single possible combination must happen, not just once, but an infinite number of times. This is not just a philosophical idea, it is a direct consequence of probability applied to an infinite canvas. Think of a deck of cards, shuffle it enough times, and you will eventually get the same sequence again. Now imagine the entire cosmos as that deck, but one with an unimaginable number of cards. In an infinite universe, every possible shuffle of particles must occur. Somewhere far beyond what we can ever see, there is a region of space where another Earth formed under an identical sun. On that Earth, a person who looks exactly like you is listening to this very sentence, perhaps wondering the same thing about their own cosmic double. These regions are known as Hubble volumes, spheres of space defined by the distance light has had time to travel since the beginning. We are forever trapped inside our own, unable to see beyond its edge. But if the whole universe is infinite, then there are an endless number of these Hubble volumes, each a self-contained observable universe. In some, the conditions are so similar to ours that your life is being mirrored almost perfectly. In others, the differences are subtler, a single different choice made years ago creating a divergent timeline. This is not science fiction, but a straightforward, if staggering, implication of infinity itself. The infinite cosmos is not the only place we find hints of other worlds. There is a layer of reality far stranger, operating on a scale so small it defies common sense. This is the quantum realm, where particles can be in two places at once, and the very act of observation seems to change the outcome. To understand this, we need to talk about a famous and slightly unsettling thought experiment involving a cat. A cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers, releasing the poison. According to traditional quantum mechanics, until we open the box and look, that atom is in a state called superposition. It has both decayed and not decayed at the same time. This means the poor cat is, in a sense, both alive and dead, a ghostly mixture of both states. This paradox was meant to highlight the absurdity of applying quantum rules to the everyday world. But a young physicist named Hugh Everett saw it differently in the 1950s. He proposed a solution so radical it eliminated the paradox entirely. He suggested the wave function, the mathematical description of all the possible states of a quantum system, never actually collapses when we make a measurement. Instead, it splits. At the moment of that quantum decision, the single universe branches into two. In one universe, you open the box and find a living cat purring and unharmed. In the other parallel universe, an identical version of you opens an identical box and finds a tragic outcome. Both realities are equally real, they just can no longer interact with each other. This is the many worlds interpretation. It means every single quantum event, every flicker of a particle, every random decay, is not a roll of the dice but a fork in the road. For every possible outcome, a new universe is created to accommodate it. Your life is a constant, invisible storm of these branches. Every time an electron changes its orbit or a photon bounces off a mirror, the cosmos is duplicating itself. The you reading this script made a choice to watch this video, but in another branch, a different you decided to do something else entirely, and that reality is just as valid as this one. The multiverse is not just out there in the vastness of space, it is being generated here and now with every passing moment. The branching of our own reality is not the only engine driving the multiverse. To find the next piece of the puzzle, we must rewind time to the very first moments of existence. Our universe began not with a slow expansion, but with an unimaginable growth spurt. In a fraction of a second, a speck of space smaller than an atom was stretched to a size larger than our entire observable cosmos. This is cosmic inflation, a theory that solves many mysteries about the universe's structure. But the most profound implication is what it suggests about the greater whole. Imagine a pot of water just beginning to boil. Bubbles form, expand, and drift apart. According to some versions of inflation, our entire universe is just one such bubble in an eternally frothing cosmic sea. The inflationary process that created our bubble never truly stopped everywhere. It is eternal. In the vast, stretching fabric of apparent reality, new pocket universes are constantly budding off, each one a self-contained cosmos with its own random set of physical laws. The force driving inflation, known as the inflaton field, is like a hillside covered in ball bearings. Our universe formed when one ball came to rest in a valley, its energy transforming into the matter and radiation we see. But the hillside is vast and other balls are still rolling, causing space to inflate at an endless, blistering pace. Wherever one finally settles, a new bubble universe pops into existence. This means the multiverse is not static, but a living, breathing entity continuously giving birth to new realities. In this eternal inflation, every bubble is a separate experiment. The strength of gravity, the mass of an electron, the very number of dimensions could be different in each one. We simply live in a bubble where the constants are just right for atoms, stars, and life to form. This cosmic foam is the ultimate laboratory, and we are the product of one successful trial run. The quantum realm and cosmic inflation are not the only paths to multiple realities. A deeper, more fundamental theory of physics points to an even more immense multiverse, one with a nearly infinite variety of laws. This theory suggests the very building blocks of our universe are not tiny points, but unimaginably small, vibrating loops of energy called strings. Think of a guitar string. Pluck it one way and you get one note, pluck it another and you get a different pitch. In string theory, these tiny fundamental strings vibrate at distinct frequencies, and each different vibration produces a different kind of particle. The electron is one note, the quark is another, the photon yet another. This elegant idea promises to unify all the forces and particles of nature under one mathematical roof. But this beautiful symphony comes with a staggering requirement. For the math to work, these strings cannot simply vibrate in the three spatial dimensions we know. They need room to move, requiring extra, hidden dimensions of space, curled up into shapes so small we could never perceive them. The specific way these extra dimensions are folded determines the resonant notes the strings can play. And that is where the gateway to the multiverse swings wide open. The possible shapes for these extra dimensions are not unique. Physicists have discovered a vast number of stable configurations, a cosmic landscape of possibilities. Each distinct shape produces a different set of physical laws, a different universe with its own unique constants. The strength of gravity, the masses of particles, even the number of fundamental forces could all be different depending on the geometric twist of these hidden dimensions. This is not just a handful of alternate realities. The number of possible stable configurations in this string theory landscape is a figure so vast it defies human comprehension. It is estimated to be 10 to the power of 500. That is a 1 followed by 500 zeros. To grasp that number, consider that the total number of atoms in our entire observable universe is only about 10 to the power of 80. The string landscape contains more potential universes than there are atoms in billions upon billions of our cosmos. We are not living in a specially designed universe. We are simply inhabitants of one possible bubble in this cosmic landscape where the vibrational notes of strings accidentally produce the right conditions for stars, planets, and life to emerge. The multiverse, in this view, is a static, eternal library of every possible physical law, and our existence is just one line in one book on an endless shelf. Mathematics itself might be the ultimate reality. This is the startling claim behind the mathematical universe hypothesis, a concept championed by physicist Max Tegmark. He proposes that our physical world is not just described by math, which we already know to be true, but that it is a mathematical structure. Think about the world of a video game. To you, it looks like a three-dimensional landscape with characters and objects, but at its core, it is nothing but pure code, a set of logical rules and equations running on a computer. Tegmark suggests our universe is fundamentally the same. The stars, planets, and even you are not the base layer of reality. You are a manifestation of an underlying mathematical pattern. If this is true, the consequences for the multiverse are profound and inescapable. It means that every mathematical structure that can exist does exist. Our cosmos, governed by the specific equations of general relativity and quantum field theory, is just one possible structure, but there are countless others. There is a universe where space has 4 dimensions instead of 3. There is a reality where the number pi has a different value. There is a cosmos built on the rules of Euclidean geometry alone, without the curvature of space-time that Einstein discovered. In this view, the multiverse is not just a collection of similar physical realms. It is a complete library of all logical possibilities. Every story that can be written with the language of mathematics is being told in some corner of existence. Our particular universe feels real and unique to us simply because we are self-aware patterns within its specific set of equations. We are like characters in a novel who suddenly realize they are made of words and that every other book on the infinite shelf is just as real. The mathematical cosmos is one of pure logic, but a more violent and dramatic gateway to other realities might lurk in the darkest corners of our own. We find it in the terrifying phenomenon of a black hole. When a massive star collapses under its own weight, it can crush itself into a point of infinite density, a singularity shrouded by an event horizon from which not even light can escape. This is the point of no return. Conventional physics breaks down completely at the singularity, its equations spewing out infinities that signal our understanding has reached its limit. But some theorists, like the esteemed physicist Lee Smolin, propose a radical idea. What if that point of infinite collapse is not an end but a new beginning? Imagine a piece of space being squeezed so violently, with such immense pressure and energy that it rebounds. This cosmic bounce could be a new Big Bang, birthing an entirely new universe inside the black hole. In this view, every black hole in our cosmos could be a womb for a new reality. The matter and energy that fall in are not destroyed, they are transformed, becoming the seed for an entire new cosmos expanding into its own set of dimensions. This is the theory of black hole cosmology. The laws of physics in this daughter universe would not be an exact copy of our own. The process is chaotic, a violent reset. The fundamental constants, like the strength of gravity or the mass of an electron, could be randomly shifted during the rebirth. Our universe, with its perfect balance for life, might itself be the offspring of an ancient black hole in a parent cosmos. This creates a breathtaking possibility, a form of cosmic natural selection. Universes that produce more black holes give birth to more daughter universes. Over a grand, multi-cosmic timescale, universes fine-tuned to create black holes would become more common. It is a haunting thought that the silent, destructive behemoths dotting our galaxy might not be tombs but cradles for countless new worlds. The silent afterglow of creation holds a secret. Spread evenly across the entire sky is the cosmic microwave background, a faint whisper of heat left over from the Big Bang. For the most part, this ancient light is remarkably uniform, a smooth sea of microwave radiation. But nestled within that sea are tiny, puzzling ripples, and one anomaly stands out as profoundly strange. Astronomers call it the cold spot, a vast region of space that is significantly colder than its surroundings. It is not just a little bit chillier, it is a colossal void of cold on a scale that defies easy explanation. Standard cosmology struggles to account for it. Perhaps it is a giant supervoid, an immense emptiness in the cosmic web where galaxies are strangely scarce. Yet even that explanation feels insufficient for the sheer size and coldness of this spot. This is where the multiverse offers a breathtaking alternative. Imagine our universe as one bubble in the eternal inflationary foam. In its earliest, most energetic moments, our bubble was not completely isolated. As it expanded at a furious pace, it might have brushed against the edge of a neighboring bubble universe. The collision would have been a cataclysmic event, a tremor rippling through the very fabric of space-time. That impact would have drained energy from the region of contact, leaving behind a permanent scar, a cosmic bruise frozen in the ancient light. The cold spot could be the ghostly imprint of that long-ago encounter, the first potential observational evidence that we are not alone in the greater multiverse. It is a fossil from a time before time, a shadow cast by a reality that is not our own. Other, smaller anomalies in the background radiation also resist simple explanation, hinting that our universe's birth was not a perfectly solitary event. The idea transforms the entire sky from a map of our past into a potential window to other worlds. We are not just looking at the origin of everything we know, we might be gazing directly at the wall of a neighboring cosmos. The universe appears to be perfectly calibrated for our existence, a fact that has left scientists both awestruck and deeply puzzled. Consider the force of gravity. If it were even slightly stronger, the universe would have collapsed back on itself in a fiery crunch moments after the Big Bang. If it were a fraction weaker, matter would have flown apart so rapidly that stars and galaxies could never have coalesced from the primordial gas. The same incredible precision applies to other fundamental numbers, like the strength of the nuclear force that binds atoms together. If this force were a little different, stars would be unable to forge the carbon and oxygen that are the essential building blocks of life. The universe seems to have won an impossible cosmic lottery, with every single dial set to an exact value that allows for complexity and consciousness. This is the mystery of fine-tuning. The odds of all these constants aligning by pure chance are so astronomically small. It is like throwing a dart from across the galaxy and hitting a bullseye the size of a single atom. One compelling explanation for this perfection is that we are not looking at a single designed universe, but at one lucky winner in a cosmic sea of failures. This is where the anthropic principle enters the stage. It is a simple yet profound idea. The universe must be compatible with our existence because we are here to observe it. We could not possibly find ourselves in a universe that cannot support life. Imagine a vast, infinite multiverse where every possible combination of physical laws and constants is realized. In most of these universes, the numbers are all wrong. Gravity is too strong or the nuclear force is too weak. These are dead universes, empty voids or fleeting flashes of energy where atoms never form and life is impossible. But in a tiny, tiny fraction of these countless realities, the numbers line up just right. We do not live in a special universe, we live in one of the rare, habitable ones. The multiverse offers a powerful answer to the question of why our world seems so perfectly tailored for us. It is not tailored at all. We are simply the lucky inhabitants of the one cosmic neighborhood where the conditions allowed us to arise and ask the question in the first place. Our own reality might be an illusion, a magnificent projection cast from the edge of space. This is the holographic principle, a theory that redefines the very nature of existence. It began as a solution to a deep puzzle about black holes. Physicists discovered that all the information describing the matter that falls into a black hole is not lost forever inside. Instead, it becomes encoded on the black hole's event horizon, the point of no return, as tiny, fundamental bits of information. Think of the event horizon as a spherical shell surrounding the singularity. This two-dimensional surface stores a perfect description of everything that ever fell into the three-dimensional interior, like a cosmic DVD encoding an entire movie. The mind-bending leap is that this might be true for our entire universe. The three-dimensional world we experience, with its galaxies, stars, and people, could be a holographic projection from a two-dimensional surface at the cosmic horizon, far beyond what we can ever see. We are the movie, and the information for our reality is stored on a distant screen. If this is true for our cosmos, then every other bubble universe in the grand multiverse would operate by the same rules. Each one would be a self-contained hologram with its own two-dimensional boundary holding the complete code for its three-dimensional interior. These realities would not be stacked like layers in a cake. They would be separate informational films, each projecting its own unique universe with its own laws of physics. The holographic principle suggests the ultimate multiverse is not a collection of places, but a library of cosmic blueprints. We are not living in a solid world, but reading from a script written on the farthest wall of space. This line of thinking leads to a deeply personal and unsettling experiment of the mind. A scientist sits in a chamber with a device linked to a radioactive atom. Each minute, the device checks if the atom has decayed. If it has, a lethal mechanism is triggered. If it has not, the scientist survives and the experiment resets. In the single universe of traditional physics, the scientist's luck will eventually run out. But in the many worlds interpretation, something profoundly different occurs. Every time the quantum measurement happens, the universe splits. In one branch, the scientist dies. In the other, they live. From the scientist's own subjective point of view, they can only ever be aware of the branches where they continue to exist. They pull the trigger again and again, and from their perspective, they always survive. They witness an impossible string of luck, a personal experience that seems to defy all probability. This is the thought experiment of quantum immortality. It suggests that your conscious awareness is forever tied to the timelines where you continue to live. You will never experience your own death in a universe-ending sense, because at the moment of any fatal event, your consciousness simply follows the branching path where you, by some quantum fluke, survive. Of course, this does not mean you are invincible. In the overwhelming majority of parallel realities, your body does perish. But the singular thread of your awareness, the you that is listening right now, will always find itself in one of the rare branches where it persists. This is not a recipe for a charmed life, but a strange consequence of infinite splitting. You might find yourself in a reality where you survive a plane crash, only to be gravely injured, living on in a world that seems increasingly improbable. The experiment is a stark and personal piece of evidence for the multiverse. It transforms the concept from a distant abstraction into an intimate truth about your own existence. Your continued consciousness may be the most direct proof you have that other versions of you have already fallen away. Our reality might be a cosmic island, a solitary slice of existence adrift in a higher dimensional sea. This is the vision of M-theory, the leading candidate for a theory of everything. It proposes that everything we know, every galaxy, star, and person, exists on a three-dimensional membrane, or brain for short. Think of our universe as a single, impossibly thin slice of bread floating in a vast, higher dimensional loaf. We are trapped on this slice, able to move freely along its length and width, but completely unaware of the other dimensions, the bulk that surround us. Other slices of bread, other brains, could be floating just a microscopic distance away in a direction we cannot point to or move through. These parallel brains would be entire universes in their own right, each with their own stars, galaxies, and perhaps even life, forever separated from us by a fundamental dimensional barrier. The forces and particles of our world are like ink stains confined to the surface of our particular page. We cannot bleed through to the next page, and they cannot bleed through to us. This explains why we only perceive 3 dimensions of space, because all the forces that bind our world together are stuck to our brain. But gravity, the warping of spacetime itself, is different. It can leak, it can seep across the gap between brains, which might explain why gravity is so fantastically weaker than the other fundamental forces. Its strength is diluted as it spreads through the higher dimensional bulk. The implications become even more staggering when we consider what happens when these cosmic islands collide. If 2 brains were to drift together and smack into each other in the bulk, the transfer of energy would be unimaginable. Such a collision could have been the very event that sparked our own Big Bang. Our universe's fiery birth might not have been a singular, isolated event from nothing, but the aftermath of a titanic crash between our brain and a neighboring reality. The entire cosmic history we have pieced together, from the first moments of inflation to the formation of galaxies, could be the ripple effect from a collision with a parallel world. This means the multiverse is not just a collection of distant, disconnected bubbles. It could be a stack of realities, separated by the thinnest of margins in a hidden dimension, with our entire existence being the echo of a long-ago impact. The very nature of our reality might be a fabrication. Some of the world's most brilliant minds have seriously considered the possibility that our universe is not base reality, but an incredibly sophisticated simulation. Think of the video games we create today. Within a few decades, we have built vast, explorable digital worlds with their own internal laws of physics. Now project that trend forward 1,000 years or 1,000,000. A civilization only slightly more advanced than ours could possess computational power so vast that running entire universes as simulations would be trivial. In this scenario, our cosmos, with all its galaxies and history, is just one program running on some unimaginable computer. The implications for the multiverse are immediate and profound. Why would such advanced beings run only one simulation? They would likely run countless variations, tweaking the fundamental parameters each time to see what happens. They might run simulations to study cosmic evolution, to understand the origins of life, or perhaps simply for entertainment. Each one of those simulations is a parallel universe, a self-contained reality with its own unique set of physical laws. The fine-tuning we observe would no longer be a mysterious lottery win. It would simply be the result of the programmers dialing in the constants to see what kind of universe would emerge. We could be living in a simulation where the parameters were set specifically to allow for stars, planets, and curious beings like us to evolve. This idea forces us to confront deep philosophical questions. How could we ever know if we are in a simulation? Some physicists suggest we might find clues in the very fabric of space-time. Just as a video game has a resolution limit, our universe might reveal a pixelated structure at the smallest possible scale. Or we might find evidence of shortcuts in the code, mathematical inconsistencies that a lazy programmer left in place. The simulated universe hypothesis does not dismiss the other multiverse theories, it envelops them. The infinite cosmic library, the branching quantum worlds, the colliding brains, all could be different levels of simulation within a grander computational architecture. Our search for parallel realities then becomes a quest to understand the nature of our own existence, and to discover if we are the creators or merely characters in someone else's story. Our own cosmic story might not have started with a single, definitive bang. the universe could be locked in an endless, rhythmic dance of death and rebirth. This is the cyclic model, where the Big Bang was not the absolute beginning, but merely the latest in an infinite series of cosmic cycles. Each cycle begins with a period of rapid expansion, much like the one we observe today. Galaxies fly apart, stars burn out, and the universe grows cold and dilute over trillions of years. But instead of fading into eternal darkness, a mysterious force, perhaps a form of dark energy, undergoes a transformation. It begins to pull the entire cosmos back together. In a great reversal, the expansion halts. Galaxies, then stars, and finally atoms are drawn toward a cataclysmic convergence. All matter and energy are compressed into an incredibly hot, dense state, a fiery seed that looks remarkably similar to the traditional Big Bang singularity. From that seed, a new universe bursts forth, resetting the cosmic clock. This cycle of expansion and contraction, known as the Big Bounce, could have been repeating forever, with no start and no end. With each new cycle, the conditions are not perfectly replicated. The fundamental constants of physics could receive a tiny, random tweak during the violent rebirth. One universe might have a slightly stronger force of gravity, the next a different mass for the electron. Over an endless succession of cycles, every conceivable combination of physical laws would eventually be realized. This creates a different kind of multiverse, not one of branching paths or simultaneous bubbles, but a sequential one, a chain of universes stretching infinitely into the past and future. We exist in one link of that chain, a universe where the constants allowed for our form of life. The cycle before ours might have been a barren, short-lived flash, and the next one could be a cold, empty void. Our reality is not a solitary event, but one frame in an infinite cosmic film, forever looping and forever changing. Your own conscious mind might be the engine that creates reality. We often think of observation as a passive act, simply noting what is already there. But in the bizarre world of quantum mechanics, the observer plays a far more active and mysterious role. Before a particle is measured, it exists in a blurry cloud of potential, a superposition of all its possible states. It has no definite location, no definite spin. It is only when a conscious observer or a measuring device that will ultimately be read by a conscious being checks on it that this cloud collapses into a single, solid fact. One moment there is a haze of possibilities, the next there is a particle in one specific place. This is the quantum observer effect. The question that has haunted physicists for a century is what exactly counts as an observer, and why does consciousness seem to have this special power to crystallize probability into reality? One compelling answer brings us back to the many worlds interpretation, but with a startling twist. Perhaps the wave function never actually collapses at all. Instead, your act of observation causes your own consciousness to split, becoming entangled with the particle. In one stream of awareness, you see the particle in one state. In that very same instant, a separate version of you observes the opposite result. There is no single outcome, only a branching of subjective experience. You are not causing one reality to become real while others vanish. You are simply becoming aware of which branch you are on. Every choice you make, from deciding what to eat for breakfast to looking at a quantum experiment, is not you steering a single ship. It is you choosing which of the infinite, already existing ships you will step aboard. The other ships, with all their other outcomes, continue to sail on completely real seas, carrying other versions of you who made different choices. This transforms the nature of existence from a fixed timeline into a personal, conscious journey through a garden of forking paths. The universe does not care which path you take because it grows them all. A strange and unexplained current flows through the cosmos. Astronomers have detected a bizarre phenomenon they call dark flow, a collective motion of entire galaxy clusters all rushing in the same specific direction. This is not the general expansion of the universe, which pushes galaxies apart in all directions. This is something else entirely, a coordinated drift as if a vast, unseen river is pulling them along. The sheer scale of this motion is staggering, involving thousands of clusters moving at incredible speeds toward a single point on the sky, far beyond the edge of what we can observe. The problem is, there is nothing there to pull them. Based on all the mapped matter in our observable universe, there is no known concentration of mass, no supercluster massive enough to generate such a powerful and uniform gravitational tug. It is as if you are standing in a room feeling a steady, persistent breeze, yet all the windows and doors are sealed shut. So where is this wind coming from? The most thrilling possibility is that the source of this pull lies outside our universe altogether. Imagine our cosmos as a ship sailing on a calm sea. We feel the expected motions, the waves and the wind, but then we notice a persistent current pulling us steadily toward a distant, unseen shore. That shore could be a neighboring universe, a massive structure residing in the greater multiverse just beyond our cosmic horizon. Its immense gravity, leaking through the fabric of space-time, could be reaching across the void and gently shepherding our galaxy clusters on a journey we cannot fully comprehend. This dark flow is not just a curiosity, it is a potential compass needle pointing toward a reality that is not our own. It suggests that the emptiness beyond our vision is not empty at all, but filled with the gravitational whispers of other worlds, forever pulling us toward the great unknown. The quantum world holds a stubborn mystery at its very core. We can predict probabilities with incredible accuracy, but the theory remains strangely silent on what actually happens in that final, decisive moment. This is the problem of wave function collapse, a deep fissure in our understanding of reality. The wave function is the mathematical description of a quantum system, a formula that encapsulates all the possible states a particle can be in, from its position to its spin. According to the standard textbook interpretation, this wave function exists in a blurred state of superposition, holding all possibilities at once until the instant it is observed. Then, in a process no one can properly explain, it violently collapses, choosing one single reality from the infinite menu of options. What triggers this collapse? Is it the measuring device, the physicist's eye, the spark of consciousness itself? The theory provides no answer, leaving a ghost in the machine of quantum mechanics. This is where the many worlds interpretation offers a breathtakingly simple solution. It removes the ghost by removing the collapse entirely. Hugh Everett's radical insight was that the wave function never actually collapses. It simply evolves smoothly and deterministically, following the elegant equations laid down by Erwin Schrödinger himself. When a measurement occurs, the universe does not make a choice. It makes room for every choice. The single, fuzzy reality cleanly branches into multiple, sharply defined worlds, each one realizing a different possible outcome. The act of observation is not you forcing the universe to pick a card. It is you discovering which branch of the multiverse you are now standing on. Parallel universes are not an added complication to this view. They are the necessary, inescapable consequence of taking the mathematics of quantum mechanics at face value. By eliminating the problematic and arbitrary collapse, we get a more coherent and simpler theory, one that paints a picture of a reality endlessly dividing, a cosmos of limitless possibility where every potential is forever realized. The relentless forward march of time might feel like an undeniable fact of our reality, but its origins are one of physics' deepest mysteries. Why do we remember the past and not the future? Why does an egg, once scrambled, never unscramble itself? This one-way street of existence is known as the arrow of time, and its direction is set by a single, powerful concept: entropy. Entropy is the measure of disorder in a system. The universe, left to its own devices, always moves from a state of order to a state of chaos, from low entropy to high entropy. A sandcastle on a beach is a delicate, ordered structure, Over time, the wind and waves will break it down, scattering the grains evenly across the shore. That is entropy increasing. The entire cosmos is doing the same thing, slowly but surely unraveling from the concentrated, highly ordered state of the Big Bang toward a final, lukewarm equilibrium known as heat death, a state of maximum disorder where nothing ever happens again. This presents a profound puzzle. For the arrow of time to point forward, the universe must have started in an incredibly special, low-entropy state. It was like a room that was perfectly and immaculately clean at the moment of creation and has been getting messier ever since. The odds of such a pristine, orderly beginning are astronomically small, like finding a single, perfectly sorted deck of cards in a mountain of shuffled ones. So why did our universe begin in this spectacularly unlikely condition? The multiverse offers a breathtaking answer. Picture an eternal, larger reality where the average state is one of maximum entropy, a vast, lifeless, and chaotic soup where nothing of interest ever occurs. In such an infinite, high-entropy multiverse, rare statistical fluctuations are inevitable. Every so often, by pure chance, a small pocket of space will spontaneously fluctuate into a state of low entropy, just as a pot of still water might, for a single moment, form a perfect whirlpool. Our Big Bang was not a singular, special creation event. It was one of these rare, random fluctuations into order. In this view, our entire cosmic history, from the first stars to the rise of life, is just a temporary bubble of structure in an otherwise formless and timeless eternity of disorder. We do not live in a universe that is uniquely designed with a forward-pointing arrow of time. We live in one of the rare pockets where such an arrow could even exist, a statistical glitch that allowed for the emergence of history, memory, and ourselves. The reason we perceive time flowing forward is simply because we could not possibly find ourselves conscious in the vastly more common regions of the multiverse where time has no meaning and life is impossible. The true shape of our cosmos might be stranger than any map we have ever drawn. For centuries, we pictured the universe as an infinite, flat sheet of space, stretching forever in all directions. But geometry tells us there are other possibilities. Our universe could be a vast, closed sphere, a four-dimensional balloon. If you traveled in one straight line for long enough, you would eventually end up right back where you started without ever hitting an edge. Or it could be shaped like a saddle, a hyperbolic space that curves away from itself, creating a landscape of infinite complexity. For a long time, the leading data suggested our universe is geometrically flat, but this does not necessarily mean it is shaped like an infinite plane. A flat geometry can fold back on itself. Think of your favorite video game. The character runs off the right side of the screen and instantly reappears on the left. The world is finite and has borders, but its topology, its connectedness, creates the illusion of an endless landscape. Our universe could be built on the same principle. It might be a giant, multi-dimensional torus, a cosmic donut. On the largest scales, space could wrap around in a complex, multiply-connected pattern. This is not just a mathematical curiosity. It would mean that if you had a telescope powerful enough to peer across the cosmos, you would not see an endless void. You would see repeating patterns. You might gaze so far into the depths that you see the back of your own head, or a duplicate of our own Milky Way galaxy, an image of our local space from a different angle and a much earlier time. In such a universe, the light from ancient stars would have taken multiple laps around the whole of creation, creating ghostly echoes of the same structures in the sky. This single, finite cosmos would perfectly mimic a vast, infinite multiverse. Every possible arrangement of matter would not need an entirely separate realm to exist. In a sufficiently large but finite wrapped space, every possible configuration would eventually repeat. There would be a region of space that is a near-perfect copy of our own solar system, with a near-perfect copy of Earth and a near-perfect copy of you. These would not be parallel worlds in the quantum sense, but cosmic echoes, the same pattern recurring again and again within the closed loops of a single, astonishingly intricate reality. We have been searching for signs of this wrapping, looking for matching circles in the cosmic microwave background, identical patterns on opposite sides of the sky that would betray the universe's true, finite topology. So far, the search has come up empty, but the possibility remains. The grandest multiverse of all might not be out there, but right here, folded into the hidden seams of our own home. The quantum world is a realm of pure potential, a place where an electron is not a single point but a smear of probabilities. Yet we never see this blurriness in our everyday lives. Your coffee cup sits firmly on the desk, not in a ghostly superposition of being both on the desk and on the floor. Something must happen to transform this fog of possibility into the solid, predictable world we experience. That something is called quantum decoherence, and it is the quiet, continuous process that carves our single reality from the infinite multiverse. Think of a perfectly still pond. If you drop a single pebble, it creates a clean set of ripples expanding outward. This is like a quantum particle in isolation, its wave function a pure, coherent state of all possibilities. Now imagine a torrential downpour. The surface of the pond is churned into chaos by millions of raindrops. The original, clean ripple pattern is instantly lost, swallowed by the overwhelming noise of the environment. This is decoherence. A quantum system, like an atom, cannot exist in a vacuum. It is constantly bombarded by photons of light, by air molecules, by the faint whisper of gravitational fields. The moment it interacts with even a single photon from the environment, its pure quantum state becomes entangled with that photon. The information about its superposition leaks out into the world, spreading at the speed of light. From our perspective, the superposition vanishes. The particle appears to snap into one definite location. But in the many worlds view, nothing has vanished at all. The entire system, the particle plus the environment, has simply split into multiple, non-interacting branches. In one branch, the environment recorded the particle being in position A. In another, equally real branch, the environment recorded it in position B. Decoherence is the mechanism that rapidly and permanently separates these branches, like a zipper sealing off parallel timelines from one another. It explains why you never see a blurry, half-alive, half-dead cat. Your act of looking at the cat is the final step in a long chain of decoherence events involving air molecules, light particles, and the atoms of the box itself. By the time the signal reaches your brain, the branching is complete. Your consciousness simply becomes aware of which branch you are on. We are not living in a single, collapsing universe. We are surfing a single, stable reality that has been carved out for us by the relentless noise of existence, forever separated from the other versions of ourselves by the silent, impenetrable wall of decoherence. The solidity of the world around you, the very weight of your own body, is a cosmic accident. This tangible reality hinges on an invisible field that permeates all of space, the Higgs field. In the first searing moments after the Big Bang, this field was in a state of perfect symmetry, a kind of featureless, energy-less plane. As the universe expanded and cooled, it underwent a dramatic transformation known as symmetry breaking. Think of a pencil balanced perfectly on its tip. This is an unstable, symmetrical state. The slightest vibration will cause it to fall, breaking the symmetry and choosing one specific direction to point. The Higgs field underwent a similar cosmic tumble. It fell from its high-energy state into a stable, low-energy valley, and in doing so, it acquired a non-zero value everywhere. This is the moment particles gained mass. As fundamental particles like electrons and quarks move through this cosmic molasses, they interact with the Higgs field, and that interaction is what we experience as mass. Without this specific broken symmetry, particles would forever zip through the universe at the speed of light, never clumping together to form atoms, stars, or planets. Our universe would be a formless, featureless sea of radiation. This leads to a staggering possibility. The way our Higgs field broke, the specific valley it settled into was not preordained. It was a random quantum decision. In the grand landscape of the multiverse, other pocket universes experienced this symmetry breaking differently. In some, the Higgs field never broke symmetry at all. Those are the barren, massless realms where nothing can ever form. In others, it broke in a way that gave particles vastly different masses. Imagine a universe where the electron is 1,000 times heavier. Chemistry would be impossible, atoms could not bond, and the universe would be stillborn. In yet another branch of reality, the symmetry breaking could have created not one, but several different Higgs-like fields, giving rise to entirely new fundamental forces that we cannot even conceive of. The existence of our particular world, with its specific particle masses and forces, is not a law of nature. It is a single roll of the dice in a cosmic casino with an infinite number of tables, each offering a different game with entirely different rules. We simply live at the table where the rules accidentally allowed for us to be dealt a hand. The ancient Greeks proposed a profound idea that anything which can exist does exist. This is the philosophical principle of plenitude, a belief that the cosmos, in its infinite richness, leaves no possibility unfulfilled. For centuries, this was a beautiful, abstract thought. Today, modern cosmology is turning it into a scientific framework. The multiverse is the ultimate expression of this ancient principle, a cosmos so vast and varied it contains every conceivable form of reality. Think of a library that does not just contain every book that has been written, but every book that could possibly be written, with every combination of letters, every plot, every character. The principle of plenitude suggests our reality is that library. If a universe can have 3 dimensions, then one does. If it can have 17, then one does. If a universe can be made entirely of purple jelly, then somewhere it is. This is not about what is likely or what seems reasonable to our limited human mind. It is a statement about the fundamental nature of existence. A cosmos that is truly complete must manifest every single logical possibility. We find ourselves in a universe governed by specific, consistent laws, not because these are the only laws, but because these are the ones that allow for observers like us to arise and ponder the question. The silence of deep space is not an emptiness. It is the white noise of a near-infinite channel of cosmic television, each one broadcasting a different show with entirely different rules. The principle of plenitude transforms the multiverse from a scientific hypothesis into a philosophical necessity. It argues that the existence of our particular, finely tuned world is not a miracle but an inevitability. In a reality that embraces all possibilities, our world was not just possible, it was absolutely guaranteed. Our everyday intuition about chance completely shatters in an infinite cosmos. We think of probability in terms of likelihood, a spectrum from impossible to certain. But in a truly limitless multiverse, this entire concept is turned on its head. An event with a 1 in a trillion chance is not just unlikely, it is an absolute guarantee. In fact, it will happen not just once, but an infinite number of times. Every conceivable event, no matter how outlandish or bizarre, is not merely possible. It is a statistical certainty playing out somewhere in the grand cosmic expanse. Think of the most improbable thing you can conceive, a bolt of lightning striking the same spot 10 times in a row, a deck of cards shuffled into perfect numerical order by random chance. A single, complex living cell spontaneously assembling from a primordial soup. In our limited, finite experience, we would call these events miracles or flukes, so unlikely they might as well be impossible. But in an infinite reality, they are not flukes at all. They are inevitabilities. The mathematics is brutally simple. Infinity multiplied by any number greater than 0 is still infinity. So if there is even the tiniest, non-zero probability of an event occurring, then given an infinite number of trials, its occurrence becomes not just probable but guaranteed. This transforms the nature of reality from a place of chance into a place of plenitude, where every story that can be written is being told. Somewhere, a planet made entirely of diamond orbits a pulsar. Somewhere, a perfect replica of the Roman Empire never fell and rules a galaxy. Somewhere, a version of you is living a life that is identical in every way, except for a single, different choice made decades ago. And somewhere, a version of you is living a life so radically different it would be unrecognizable. The infinite multiverse does not discriminate between the probable and the improbable. It hosts them all with perfect, silent indifference. This means the universe is not just stranger than we imagine. It is stranger than we can imagine, because every single one of our wildest imaginations is already a concrete reality in a cosmos without end. This recurring theme is no coincidence. The multiverse does not spring from a single, speculative theory. Instead, it emerges as a common, almost inevitable, prediction from several of our most robust and successful pillars of modern physics. These are not fringe ideas, but frameworks that have passed countless experimental tests and made stunningly accurate predictions about our world. The existence of other realities is not the starting assumption, but a startling consequence of taking our best science seriously. Consider cosmic inflation, which perfectly explains the uniformity and structure of our cosmos. The math of eternal inflation does not merely allow for other universes, it demands them, creating an endless froth of bubble realities. Or look at quantum mechanics, a theory whose equations have been verified to an almost absurd degree of precision. The standard interpretation, with its mysterious wave function collapse, is philosophically messy. The many worlds interpretation, by contrast, follows the clean, unadulterated math to its logical conclusion, a reality that perpetually branches. Even string theory, our most promising candidate for a theory of everything, describes a vast landscape of possible universes, each with different physical laws. When three of our most powerful scientific descriptions of reality, born from entirely different lines of inquiry, all point toward the same breathtaking conclusion, we must listen. It is a convergence of clues, a chorus of evidence whispering that our universe is just one verse in an endless cosmic poem. The greatest battle in modern physics is a silent war between two titans. On one side stands general relativity, Einstein's magnificent description of gravity as the curvature of spacetime, governing the dance of planets and the expansion of the cosmos. On the other side is quantum mechanics, the rulebook for the subatomic world, a realm of probability and uncertainty. Each theory is spectacularly successful in its own domain, but when they meet, they produce nonsense. At the center of a black hole, or in the first instant of the Big Bang, where gravity becomes incredibly strong on a tiny scale, the equations of both theories break down, spitting out infinities that scream of our ignorance. Uniting these two pillars into a single, coherent framework, a theory of quantum gravity, is the holy grail of physics, and the path to that grail seems to lead directly through the multiverse. One leading contender is loop quantum gravity. This approach suggests that space itself is not a smooth, continuous fabric, but is woven from tiny, indivisible loops a billion times smaller than an atom. Think of the fabric of spacetime as a chainmail shirt, each tiny link a loop of quantized space. This has a breathtaking implication for the origin of everything. In this model, the Big Bang was not a true beginning, it was a rebound. A previous universe, perhaps similar to our own, collapsed under its own gravity. But instead of crushing itself into an infinitely dense point, it met the resistance of these fundamental space loops. The universe bounced like a ball hitting a solid floor, and the energy of that collapse fueled the expansion of our own cosmos. This is the Big Bounce, a cyclic model of the universe. If this is true, then our universe is just one link in an endless, timeless chain of cosmic cycles. Each bounce could slightly tweak the fundamental constants, creating a sequential multiverse where every possible set of physical laws is realized across an infinite series of universes. The quest for quantum gravity does not just look backward, it redefines the nature of reality itself, suggesting our entire cosmic history is merely one chapter in an infinite cyclical book. The profound silence of the cosmos is one of its greatest mysteries. We gaze out at 100 billion galaxies, each with 100 billion stars, and we hear nothing. The Italian physicist Enrico Fermi famously captured this paradox with a simple, devastating question. Where is everybody? If the universe is so vast and old, it should be teeming with intelligent life. Yet our telescopes and radios have found only an unbroken silence. The multiverse offers a startling and humbling answer. Perhaps we are not living in a typical universe at all. We may reside in a cosmic backwater, one of the rare, quiet neighborhoods in the grand expanse of the multiverse. In most other realities, the conditions for life of any kind might be impossible. The fundamental constants could be wrong, preventing the formation of stable atoms or long-lived stars. But in a smaller subset of universes, life does emerge. And within that subset, an even tinier fraction might give rise to intelligent, technological civilizations like our own. In some of those worlds, alien empires could flourish, filling their skies with ships and their radio bands with communication. But their signals cannot travel between the bubbles of the multiverse. They are trapped in their own cosmic pocket, just as we are trapped in ours. We are not alone in the greater multiverse, but we are profoundly isolated, living on a quiet street in a city of infinite size. The silence we hear is not the silence of an empty universe, but the quiet of our own unique, and perhaps lonely, celestial home. From quantum splits to cosmic bubbles, our journey through 25 scientific reasons reveals a cosmos of staggering possibility. We have ventured from the infinite shuffles of an endless universe to the branching paths of every quantum decision. We have explored the idea of our reality as one bubble in an eternal foam, one brain in a higher dimensional stack, and even one simulation in a vast computational library. Each of these ideas, born from our most successful physical theories, points toward the same humbling conclusion. We may never peer directly into a neighboring universe, but the evidence for their existence is woven into the very fabric of our understanding, from the mysterious cold spot in the ancient sky to the unsettling flow of dark matter. The multiverse is not a wild fantasy, but a profound implication of taking our best science to its logical extreme. It suggests that every story that can be told is being told in a near-infinite library of realities. So the next time you make a choice, just wonder what the other you is doing right now, and tell us what you think. Share your own theories and questions in the comments below.